welcome back to the bioenergy lecture series. So, in the last class when we concluded, we talked about, we outlined the different conversion strategies currently followed, and we categorized the different conversion strategies into three groups. We talked about thermochemical conversion, we talked about biochemical or biological route of conversion, we talked about a mechanical route along with esterification, where we extract biodiesels from rapeseed, from jatropha and other sources. And within the thermochemical route, we talked about 4 different routes which are being followed, which includes combustion, pyrolysis, gasification and liquefaction. Whereas in the biochemical route, we talked about 2 techniques, digestion and fermentation. And we talked about that fermentation is a very age old technology which has been followed all over the world, and mostly in the slightly on the temperate part of the world where it is cold, where people brew wine or beer or all forms of liquors at home in their cellars, okay, where they convert wood and other things into alcohol. Whereas in terms of the digestion part, we talked about the gobar glass or cow dung, which is used in the slurry form, is used to generate the gas which is being used, gobar gas plants. And there are several other examples, and then we correlated it back with what happened through geological periods where several organic matter got trapped, and through digestion they started generating gas, and which we are deriving as a natural gas today, methane and other sources. Okay. So, today what we will do, we will come back to the chart where we left in the last class. So, this was the outline what we formed, the biomass to energy formation, and today our goal will be to understand the most primitive and the most simplistic of all processes under the category of thermochemical, which is the combustion process. So, today we will start with the combustion process. So, let us move on to the slide. So, as we do in every class, first of all we will talk about the simple combustion. Combustion is a very straightforward thing. You take a biomass, paper, vegetable waste or anything as a matter of fact, and you all have seen that the cow dung is being dried and used as a fuel. This every Indian has seen wherever they are. Each one of us has seen during the winters or any other day, people cook with woods. Okay? These are common things. So, essentially a wood is a biomass, cow dung is a biomass. So, you are burning them in the presence of air. That is all combustion is all about. So, when you are burning something in the presence of air, so you are having oxygen in the environment. So, what will happen? So, your biomass has lot of carbon, it is reacting with the oxygen of the environment, and it will generate 2 things. It will generate carbon dioxide plus heat. Now, what you do to that heat is very important, and how you can process that carbon dioxide. Okay. So, just now what I have said, let me graphically put it across for you. Well, so we are dealing with combustion, okay, and in the combustion section, so we are dealing with, say for example, so we have a biomass like this, okay. So, finite amount of biomass out here, and one of the thing you all must have observed when in the villages or in the rural places where cow dung is being used for making or being used as a fuel after drying. So, what that drying thing does, it removes the water from it. So, this brings you back to that very first point about the properties, what we talked about, intrinsic water and extrinsic water. Remember, we talked about the water concentration. So, essentially what you are doing, you are getting a biomass, a feces of a cow or a buffalo, which is rich in water. So, you are drying it in the sun, getting rid of the water, and then you are using it. So, say for example, just you can think it very simple. So, you have, let me go to the new slide. So, you have, say for example, you have cow dung. This is a good example for you to understand. So, you have two routes. One route is that you, so it has significant amount of water trapped in it, okay, plus of course carbon material, carbon and all other things, okay, carbon, hydrogen, oxygen and nitrogen, phosphorus, sodium, potassium, likewise. Okay. Now, one route is you dry this, you remove the water, and what you get is dried cow dung, which is a fuel for burning. Whereas, you can follow another route, you keep the water intact along with the water and you put it in a closed chamber, which is a biogas plant. So, what will happen in the biogas plant, because of the microbes which are present out there, this will go through a process of digestion and also certain degree of fermentation will take place, you cannot avoid it, and this is going to generate gas. So, you see with a simple example, and this gas is could be used for cooking, which most of the places in our country, especially in the rural places, we use this. Now, see with such a small simple thing, and this is mankind has been doing it since ages. It is nothing new that today only we have started it. But what is important is that these technologies have to be fine tuned with time, had to be made more efficient, and what is important here to realize, depending on the total x, say x gram or x kilogram or x ton, okay, kilogram or x ton, how much fuel we are getting out of it and how much we are losing as ash, that define the efficiency of that fuel. Okay. This is how, so this fuel when we are burning it, we are generating heat and CO2. So, coming back to the previous slide where we started, when you have the biomass out here, of course, you have to ensure if you are going for the combustion route, less than 50% water. This is very critical. So, in other words, one has to ensure that you dry up the sample significantly, that at least 50% water or more than 50% of water is lost. Otherwise, this is not suitable for combustion. Now, what you do, you burn this in the presence of air. So, you have the air or oxygen, in the presence of oxygen you are burning it. What you are generating is, of course, apart from carbon dioxide, because this has lot of carbons out here, carbon dioxide which is getting to the environment, which is a tricky thing of course, and that is where we talk about a lot of carbon capture. What you are generating is heat. Okay. Now, this heat what you are generating could be utilized for several things. What you can do with this heat is you can use this strategy to develop a stove, which is the most simplistic of all. You can develop a furnace, okay. You can develop a boiler. We will talk about a little bit about boiler later. You can put it in the steam turbines. Okay. Similarly, we can put it in the turbo generators. These are the different, at least to name a few, what you can do. And what you are essentially doing, if you remember the last class, last to last class, you are breaking these bonds, and these bond energies are, so this chemical bond energy is liberated in the form of heat energy. Okay. This is how we carry out the process. Now, while you are running them, running say a boiler or a steam turbines or something, what you are essentially doing, you are converting the heat through the steam, and we will talk about this boiler design and everything in a sec, at least briefly. So, just before I get into this, what is important here to know is that this combustion process, what is happening out here, right? This whole combustion process, this combustion produces huge amount of hot gas, which is of course a lot of it is rich in carbon dioxide at around 800 to 1000 degrees centigrade. Okay. Now, the question is coming back. The question is, what kind of combustion plants are we talking about? The combustion plants, if we talk about, it could be as simple as very small scale for the domestic use or domestic heating, very small scale for domestic use or domestic heating purpose, or it could be as large as 100 to 300 megawatt large scale industrial plant. Okay. So, this is the conversion, but interestingly most of this, if you look at their efficiency, as I was telling you, the efficiency is around 20 to 40%. Net bioenergy conversion efficiency in the power plant ranges from 20 to 40%. Whatever, whether it is a small, whether it is a large plant. One of the ways by which one can really increase this combustion plant efficiency is co-combustion of biomass. Now, we will talk about this, what does that mean? Co-combustion of biomass in coal fired power plant. Okay. So, what is coal fired power plants? Okay. Before we get into the coal fired power plants, we will talk just a little bit about the heat. So, what we are doing through combustion is we are generating a lot of heat. Okay. So, one of the ways is that you use it in one of the heat engine cycles, you can use them. You can feed this heat or fed this heat to heat engine cycles. The one example is the Stirling cycle, okay, which uses combustion to provide the shaft power. Okay. So, you are moving the shaft. So, basically what you are doing is you are converting the heat into mechanical energy, shaft power directly. But very interestingly, the development of the cycle is presently limited with a small power output. Okay. Development of such cycles have limited power output. I am just putting OP as the output. Okay. Now, coming back to the combustion plants, we are talking about coal fire. I was telling you what is this coal fire combustion plants. So, combustion plants, the coal fire combustion plants are those who have never been exposed to this. First, try to understand what happens in them. So, there is a boiler, okay, it's filled with water. Underneath, you have coal. Most of this coal fire work, they grind the coal and put it there, and you heat the coal. So, as the coal is burning, the water started to boil and it generates a huge amount of steam. This steam is funneled through a tube and fed on a turbine. Because of the impact of it, the turbine starts to move, and once the turbine moves, there are generators which are there, which starts to generate, they also start to move and they generate the electricity. So, the way the schematics, let me put the schematics for you, that will make more sense. Okay. So, you have kind of a boiler sitting here. Okay. On the boiler underneath you are having this coal. In the presence of oxygen, you are heating it. So, what you are generating is lot of CO2 and lot of heat, and this heat is the one which is, so you have the water. Okay. So, if you look at it, this heat which you are generating out here is fed, which is the boiling water. This is generating a lot of steam. Okay. This steam is fed, and steam at that time, the temperature of steam, such boilers comes out to be 600 to around 600 degrees centigrade. This steam is piped through a funnel to a turbine. Okay. And the turbine blades start rotating the turbine because of the impact of it, rotating the blades of turbine, and that activates the generator rotors, and these generator rotors then generate the electricity, which follows the Michael Faraday's electromagnetic induction. Okay. So, this is the basics. Okay. Electromagnetic induction, electromagnetic induction. This is something I do not know how many of you have seen it. There are bulbs attached to the dynamos, if you have seen it. When you ride the bicycle, the bulb glows because it is the mechanical energy which is translated into electrical energy using passing it through the coils. Okay. So, just go back and check the basics, and if time permits definitely I will come back to this. But what is important here? So, the point is what I am trying to make. So, it has been observed. So, if you look at what all the inputs you are putting for generating electricity. So, you needed regular supply of coal, you needed significant amount of oxygen, these are input, I am just putting IP, okay, inputs. You need fresh boiling water all the time, and your outputs, let me put another color on that, and your outputs are, you have this steam which is an output, you have significant amount of carbon dioxide as your output, OP, okay, output, and then you have to run the turbine. So, you have to have the materials, you have to have the piping which can withstand this kind of temperature. And if we talk about a standard 500 megawatt plant, so you will realize for to run a 500 megawatt plant continuously, you need 200 million tons of coal per year. Mark this number. So, this is what is the input we are talking about, okay? And you need for a 500 megawatt power, you need 1.6 million cubic meter of fresh good quality air. This is the second requirement when we talk about the air. Okay, this is the second requirement. And what you are giving out in this whole process of burning, apart from the carbon dioxide, you guys remember we talked about the ash, there is a lot of ash which is formed, and the ash is around 200,000 ton per year. Apart from, you have CO2, you have this steam, you have 200 tons of ash, and of course, this steam is recycled back and recondensed back into water, but there is always certain amount of water which is lost in that whole process. So, the reason to give you a outlay of this is to get you a feel that where the combustion research needed the bioenergy supply. So, it has been observed that many of these combustion plant or coal plants, if along with the coal which is depleting, if you use the biomass, dried biomass, it works really good. So, simple principle. So, what you are doing, so this is the addendum to the existing. So, here the coal what you are having input, you are putting here biomass, okay. But then you have to realize biomass and coal's efficiency are different, because they have different level of water concentration, different level of composition, because this is pure carbon, 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 but here you have lot of other things. So, now automatically where you will be needing coal of the range of 2 million tons coal per year. So, automatically you have to realize that you will be needing far more amount of biomass as compared to 2 million tons of coal. So, this is to just give you a feel that where everything fits in. Currently, most of the thermal power plants across the world relies on coal, and that is how the electricity is being produced, except barring aside in US, where instead of what you see out here coal, they use for this heating, they use nuclear materials, but that also comes with its own set of problems. Okay. So, what we as a nation or as a race as mankind is trying, that how we could bypass the coal. So, we need highly efficient fuel. Of course, I mean, a dream will be something like what we have in the nuclear materials, but of course, it is a far cry today, but that is where lies our catch. So, the reason to kind of walk you over through how a thermal power plant works is like this, and these are the zone of intervention where highest quality biomass can make all the difference. Okay. So, this is overall what I wanted you people to understand about the combustion process. Here in combustion, always remember whether are you burning it in presence of oxygen or absence of oxygen. So, if we go back a little bit further up where we talked about the different routes. So, this is what we talked about in the presence of oxygen, and when we talk about the next technique, what we will be talking about pyrolysis, we will talk about in the absence of oxygen. So, I will close in here, we will take it up from here. Okay? Thank you.